So for this lesson, we'll return to the ideas of linear regression and the correlation coefficient, but with a focus on ordinal data, which is ranked data, in which we just put data in ranks as first, second, third, and so on, and looking at a different type of a correlation coefficient. So for example, here is some data showing for 7 different racers their position after 2 kilometers and at the end of the race in a 5-kilometer race. So for example, runner A was first after 2 kilometers but finished third. Runner B was second after 2 kilometers and finished second in the race, and so on. And so I don't actually know the overall times for these runners, I just know their order. So the data is not as specific as other types of data when you have just a rank of first through 7th in this point. So what we want to look at is what's the correlation between their ranking after 2 kilometers versus the end of the race. And so one option is, since we have already have all these ranks, is just to put all this data into our GDC. And one column, the X column, or the first column would be just 1, 2, 3, 4, 5, 6, 7. And then the second column would be their ranks at the end, 3, 2, 1, 5, 7, 4, 6. And if you put ranked information like this into your GDC and find the correlation coefficient as we've always done before, you should get an R value of about 0.679, which we can see is a moderate correlation. Roughly below 0.7 we call moderate correlation around there. So it's not quite a strong correlation, but a moderate correlation between their ranking after 2 kilometers compared to the end of the race, which makes sense that there's some sort of correlation here, but it's not that strong. However, we can also calculate this same correlation between rankings as long as there's no ties. By that I mean, in this case, there's no one who's tied for 4th, for example. So as long as there's no ties, we can calculate this actually fairly quickly using this formula, which is not quite as complex as it looks, although we're always allowed access to our GDC, which is 1 minus 6 times the sum of the difference between the rankings squared divided by n times n squared minus 1. So like I said, it's not quite as complex as it looks. For example, I should get the same value if I go 1 minus 6 times the sum of the difference between these. So for example, looking at runner A, at first they were first, and then by the end they were third. So that's a difference of 2. And so we want to square that. And so it's 6 times 2 squared, which is clearly 4. And I'll do the same thing for all of these. This has a no difference, so it's 0 squared. Plus, next we have a difference of 2 again. And it doesn't really matter if we go 3 minus 1 or 1 minus 3 because we're going to square it. So I'm just going to stick with the positive. So I have 2 squared. If I just work my way down all the runners, looking at the difference, then I have 1 squared plus 2 squared plus 2 squared plus 1 squared. 6 times that divided by the number of runners in this case, 7, times that same number squared minus 1. So 7 squared minus 1. And if you calculate all this, you get 1 minus this whole big rational expression here is approximately 0.3214, which is approximately 0.679. Keep in mind this formula here, which is, again, can be a little bit tedious when you have lots of values, but at the same time, it is good to be able to use it if we need to. We can only use, first of all, if it's realistic with not a lot of data to add up. Otherwise, it becomes really cumbersome, as long as there's no ties. If there are ties, we just can't use this, in which case we want to use our GDC, which is totally fine to use as well. With that said, I'm going to focus on our GDC work going on. What I have here are the top 7 new movies released in the week of November 17th to 23rd, 2023, and how much revenue they made in American dollars during that week, compared to their Metacritic score, which is an aggregate score of all the critical reviews. Essentially, the closer to 100, the more well-reviewed it was by a variety of critics. The closer to 0, the more poorly reviewed it was. And so we want to see what sort of correlation there is between the revenue these movies made in their first week compared to how well-reviewed they were, which is the Metacritic score. And I want to look at their the correlation coefficient of their ranking. Now, I should say going forwards, the correlation coefficient of ranking we usually call RS. To be honest, I probably should have said this before. It is a correlation coefficient, but we call it Spearman's correlation coefficient, or Spearman's ranking, which is mentioned right here, Spearman's rank correlation. And I realize I probably should have mentioned that already. Oh well, please forgive me. But again, it is same, closer to 1, the closer to the correlation is, closer to 0, the less of a correlation there is. And we never want to also mix up correlation with causation. Just because there's a correlation doesn't necessarily mean one causes the other. But when we see a little S, that's referring to Spearman's rank. And again, it's a correlation of the rankings, not the actual values. Because the actual values I see here for revenue are more specific than the rankings. But if I change these to rankings, well, the revenue already is ranked. So in terms of revenue, this is already 1, 2, 3, 4, 5, 6, and 7. And now for that's like my X column. For my Y column, the independent variable, I want to rank these. So the highest ranking movie here, but it's actually not that high of a rank, is Napoleon, that's first. And then second was the movie Thanksgiving. Third is the movie Saltburn at the bottom here. Fourth was the Hunger Games movie. Fifth, just barely, was the Trolls movie. Sixth was Wish, and the lowest reviewed was Next Goal Wins at 44. All right, so I'm gonna look at the correlation coefficient of these. Again, notice there are no ties. There were no two movies that had the exact same revenue nor the exact same score on the Metacritic score. So again, I could use that formula. That said, I've already kind of talked about that. And so I'll just at this point, just go to a GDC, and in which these are my first column data points. These are my second column's data points. Find linear regression, find the correlation coefficient, and we get that correlation coefficient to be about 0.179, which means that's pretty close to 0, which means we can say with a good amount of confidence that there is, at least as of this week, there is essentially no correlation between the critical review of the movie and the revenue it made. So I'll just say that there is no correlation between revenue and Metacritic score. So, with that said, the last thing I want to look at is when we do have ties. And so, if I look right here, this is showing for 10 different finalists in a free dance competition, their scores from 2 different judges. And if I just look here, the names don't really matter. No offense to the people, but this pair here, one judge gave them a 9.5, one gave them a 9.75. The next person, they were both given 9.5 by the judges, and so on. You can see how their scores compare from one judge to the other. And so I want to find, again, Spearman's rank correlation for this. And so again, the first thing I need to do is put these in order, but there will be ties here. And so let's look at judge number 1. The highest ranked person was this Hubble Donahue, so that's rank 1. But then there's a tie for the next 2. For example, I'm just going to put 2 and 3 for a moment. But they're both tied really for second place, or they're both tied for third place, however you want to look at it. So what we do here is we find the average of these 2. So I just think, okay, 2 plus 3, divide by, there's 2 of them, which is 5 over 2, which is 2.5. So each of these I think of as 2.5. And then work my way down. So next, fourth, down here with a score of 9.25, there's only one person. And then I have another tie, a 3-way tie. So I'll say a 3-way tie for 5, 6, and 7. But again, that's not actually what I'm going to do. And so I'm going to cross those out and just go 5 plus 6 plus 7 and divide by 3 this time. And I get exactly 6. So each of these we rank as a 6. Just about done. I have where am I here? Too many left. Not too many left. So I got an 8.5. So that's my person 8th. And then 9th and 10th down here are tied. And so again, I'll add them up, divide by 2, and I get 9.5. So those are the rankings for Judge 1. All right, just do the exact same thing for Judge 2. And so in this case, there's only one person who's in first. There's no ties for that. There's a two-way tie for these two. So instead of 2 and 3, sorry, I wrote that down wrong. Instead of 2 and 3, add them up, divide by 2. They're both 2.5. There's a tie for 4 and 5th down here. Add them up, divide by 2. I get 4.5. There's a tie for 6, 7, and 8. There's 3 of these 9s exactly. So 6, 7, and 8, but add those up, divide by 3. Again, we get 7. And finally, there's a tie for last, these 2. So again, I'll call them for a moment 9th and 10th, but really add them up, divide by 2. I get 9.5. And so these are the values we're going to use for our ranks. So with that said, now it should be quite quick. If I want to find Spearman's rank correlation coefficient, put these into my GDC, do the linear regression, find the value of R, and we should get a value of R of about, to 3 significant figures, 0.937, which thankfully means there is a very strong correlation between one judge and another in terms of their rankings. And I say thankfully because in terms of a competition where their aim is to be first, if not second, if not third, you want to have your judges having a strong correlation of what they considered best and so on. If there's not a strong correlation, then that would be a concern. And so again, there is a strong correlation between these two judges, which I said, that's a good thing here.